So we've gotten through most of the traditional topics in calculus, and now we're going to focus on a few special topics which are normally taught in many calculus courses, extrema and optimization. And we're introducing them side by side because the tools that we develop to analyze extrema go hand in hand with determining the maximum or minimum values of a function, which is really determining what values optimize the function. So in this module we have three different objectives. So we're going to talk about critical points, which is in this video, and in the subsequent videos we're going to talk about the first derivative test, second derivative test, and then talk about local and global extrema, and also maximum and minimum values, again getting at that idea of optimization. So let's go ahead and begin. So we define a critical point to be a point, okay, so an x comma y value, okay, c comma f of c, again x and y, for a function such that the derivative at our c value is 0 or undefined. Okay, and so the language we use to communicate this is we say the point is a critical point. Another way to say this is a critical point of f occurs at x is equal to c. It is, you cannot say, and this I'm going to put a warning symbol here, you can't say x equals c is a critical point. This is wrong, mainly because a point means a point refers to an x and a y value, a coordinate pair, if you will. And to say it's just one value is not correct. So just a careful note on our language here. So again, we want to kind of develop this reasoning. So why are these points useful? Well, they do give us more information about the graph and the function, and we'll talk about that in the next video. But in particular, I want to just step back briefly into what we discussed in precalculus. Well, precalculus, and I guess more so in Module 3 when we first introduced the derivative. So if we knew that the derivative was positive, what did we know about the original function? Well, if we know the derivative was positive, that meant that the slope was positive, meaning that the function was increasing. Okay, and that was, and you can denote it as just an upward arrow to the right. And then similarly, if it was negative, that meant that the slope was negative, or it was decreasing on an interval. Okay, and so again, shorthand, I'm probably just going to use a downward arrow from going down to the lower right. And if f prime was 0, well, that meant the slope was 0, or we just had a horizontal line. So this meant that it was just a horizontal line. Okay, so critical numbers, remember, critical numbers we define to be places or x values, critical points occur at x values where the slope is 0. Okay, so again, we're going to look for graphically horizontal lines. Okay, so again, here's a graph, and we want to determine the critical points. Well, I want to determine where the slope is 0 or it's undefined. Now remember, we said a derivative fails to exist at sharp points or at cusps. Okay, so I need to look for sharp points, and I need to look at places where I have a horizontal line, or at least a horizontal tangent line, if you will. So I'm just going to go ahead and make a list. So I'm going to just proceed going from left to right and go through this function. Okay, when I get down to 3, I would classify this as a sharp point. Okay, so I'm going to say my critical points occur at, and I'm just going to make a list here, x is equal to minus 3. Okay, so there's a critical point there, and I could actually give the coordinate, so this would be minus 3 comma minus 1. Here, this isn't necessarily a sharp point, but if I look at the tangent line is going to be horizontal, this meaning the slope at the point is 0. or at negative 1 is 0. So I'm going to also say there's a critical point at x is equal to minus 1. Okay, progressing. Okay, slope is not 0, slope is not 0, slope is not 0. Down here, I have the slope being 0, and I would also, you could also say this is a sharp point too. So I would say I'm going to have a critical point also at, or occurs at x is equal to 1. And then my last sharp point is right up here. This is a big cusp. So I'm also going to say that a critical point occurs at positive 3. Okay, so I just made a list here. Right now we're not going to do anything with it, but we will shortly. Okay, and now we want to determine these things algebraically. Okay, so remember, there were two conditions for critical points. First one was, it was where the first derivative is equal to 0, and the second one was where the first derivative does not exist. Okay, meaning, well, how do I get something to not exist? I have to have a denominator that gives me a value that results in me dividing by 0. Or there are a couple other conditions too, but that's the main one when we think about does not exist. So let's go ahead and work with this first one. So I have the function. Let's go ahead and determine its derivative. So first derivative, just by the power rule, I get 6x minus 24. Okay, and to find the critical numbers, I'm going to set this equal to 0. This one, the first derivative is a polynomial, so it exists everywhere. So this second condition, I can't actually do anything with. But I can go ahead, and I forgot a square. So I'm going to just go ahead and determine this algebraically. Factor out of 6, I get x squared minus 4 is equal to 0. And this factors as x minus 2 and x plus 2. And after I solve this, I just get x is equal to plus and minus 2. So those are my critical numbers. So I can say, or my critical points. So my critical points occur at x is equal to plus and minus 2. Not too challenging. Okay, let's go through another example. Okay, so I have a natural log of the absolute value of x squared minus 1, that quantity squared. And before I do this, again, I'm going to do some algebra because I like algebra. And also I avoid the chain rule when I do the derivative. So power rule for logarithms, bring that out front. So this is 2 times the natural log of the absolute value of x squared minus 1. And when we differentiate this, the absolute values just drop. So the derivative here is equal to, that constant stays out front, so I have 2 times the derivative of natural log of this is just 1 over whatever is inside, x squared minus 1. And then I have to multiply by the derivative of the inside part, again this is a chain, times 2x. Okay, now in this one I need to check these two conditions. So when is the derivative equal to 0 and when does it not exist? And I'm actually going to start with the second one. So I need to look at the values that produce, or the values that result in me obtaining undefined values. And that really just comes from the denominator. So my critical points occur at, well, I need to think about what makes this denominator undefined. And you can factor this and show this, but it's going to be plus and minus 1. So at plus and minus 1, I have critical points for x. In the other case, now, when this is equal to 0, this is really just saying when is the numerator equal to 0. So I'm just going to rewrite this as 4x over x squared minus 1. And so if I set this equal to 0, the denominator plays no role in this. And so I just see, okay, well, this is the same as saying, well, when is 4x equal to 0? And so I get x is equal to 0. So I also have a critical point occurring at x is equal to 0. Okay, so 2 different conditions to determine critical points. Now, right now we've just done the algebra and looked at it graphically, and in the next video we're actually going to discover more uses for critical points.